As we end our discussions on dynamics, we come back around to the whole concept of impulse and momentum. None of this is new, except that we're going to approach it in a little bit more complete aspect. We've already discussed linear momentum, and let me just point out now that linear momentum is a vector quantity, and the whole concept of vectors is super important to dynamics, and we cannot abandon those ideas. In addition to linear momentum, we have talked about angular momentum in the past, and we're going to continue to talk about it. In the past, we considered angular momentum to be r cross mv. This is still true. The fact that that's a vector cross product is, again, very critical. The magnitude of the angular momentum then might be the perpendicular component of the radius times the mass times the velocity. In other words, if the velocity of a particle is moving along this line, maybe to the right, and I'm looking at an object right here as my observer, so we'll label that O. So the angular momentum of this object, which has a mass times velocity moving to the right, will have a corresponding radius r, and as this object moves to the right, this distance right in here is the component of r perpendicular to the mass times velocity, so this is r perpendicular. And as this object moves along this straight line, r perpendicular, no matter where we are, this is r a little bit later on, r perpendicular is the same. That's not going to change as long as that object's moving along a straight line. But again, we have to consider the idea that this is just a magnitude. As far as the direction goes, r cross mv, think of mv as moving around O. It's moving around in a clockwise fashion. So in this particular example, r times mv will be negative k direction. If it's clockwise, it's in the negative k direction. But we want to add to our definition of angular momentum. We want to add this term I omega. Now keep in mind that momentum was mass times velocity, and angular momentum is going to be angular mass. It's not just the mass, it's also dependent upon where the mass is located, but it is the angular counterpart to mass times velocity, or specifically angular velocity. So angular mass times angular velocity is equal to angular momentum, just as linear mass times linear velocity was equal to linear momentum. All of those concepts that we have discussed in the past have an angular counterpart, and angular momentum is no exception to that rule. And the equation is the same, except instead of mass times velocity, angular mass times angular velocity. For just about every problem we work with, we're going to have angular momentum in the z direction, the k hat direction, and it will either be clockwise, which is negative, or counterclockwise, which is positive. You might recall when we were discussing particles in a previous chapter, impulse and momentum was defined as mass times velocity 1, or linear momentum, again a vector quantity, plus an integral of force, and very important to keep in mind, that's external forces. All internal forces will cancel out. Internal to my system. Now what is my system? That's going to depend from one problem to another. But all internal forces will cancel out. Notice this is an integral with respect to time as opposed to work, which we've discussed in the past. That was an integral with respect to position. This is the impulse right here. And that's going to equal, when I add that to the initial momentum, that's going to equal the final momentum. So this impulse, what's inside the integral, that's L2 minus L1. Again, vector quantities. When would we use this? Well, this is an integral with respect to time. So if time is what we're given, or time is what we're looking for, this will be the preferred integral as opposed to work and energy. Well, again, all of this impulse information and momentum information can be brought over to the angular world. And so my initial angular momentum plus angular force, but angular force is what we refer to as moment. And again, this is all external moments. When I integrate the external moment with respect to time, I get the final angular momentum. So this integral is angular impulse. This is h2 minus h1. This is angular impulse, just as L2 minus L1 was linear impulse. So they're the same concepts, only one's in the linear world and one is in the angular world. And both of them may be correct at the same time. In fact, we'll do some problems in a little bit that will take advantage of both of these concepts. Okay, so let's look at this example for starters. I have three gears. Gears A and B are identical. Notice they're given a mass of 675 grams. The radius of gyration is given as 40 millimeters. Gear C, however, is larger. It has a mass of 3.6 kilograms, and its radius of gyration is 100 millimeters. There is kinetic friction between the bearings of the gears, and that's going to cause a moment as opposed to a force. If we have an object, let's say we have an object sliding down an incline or sliding down the road, there's going to be a force exerted on that object, and that force is going to cause a reduction in speed, which is a change in linear momentum. In this case, I'm going to have friction again, but it's going to cause a couple or a moment, and that moment is going to reduce angular momentum, angular velocity, as opposed to linear velocity, which is what a force will change. All right, and those couples, those magnitudes are also given here, and they are constant. Notice they're the same for the two smaller gears and then larger for the bigger gear. The angular velocity of gear C at the beginning is 2,000 RPM, so I do have an initial momentum L1. Now what we're going to do in order to answer the question, when does this system come to rest, so in the end, the angular momentum of the system will be 0. What we're going to do is we're going to examine each gear separately, and then we're going to add up all the terms. So let's start off by looking at a larger gear C. Okay, so you can see that gear C is rotating in the clockwise direction, and that means that there's going to be a moment in this direction, and that moment is going to be a frictional moment due to the bearings acting on the gear. In addition, the larger gear in its rotations to the right is going to push on the smaller gear A in this direction. It's a normal force because it's between teeth. I'm going to call that FNAC. That's the normal force acting on gear A due to gear C. But keep in mind, right now I'm interested in what's going on with gear C. Well, Newton's third law says there must be an equal and opposite force in this direction, FNAC. Same term because it's the same force in magnitude but opposite in direction. And that's going to be a normal force due to gear A acting on gear C. In a similar fashion, there's going to be an FNAB here and an FNAB here. Now because A and B are identical, the normal forces will be exactly the same in both of those cases. So what that means then is that the net moment acting on gear C, so the sum of the moments acting on gear C, will be FNAC, and that's going to be in the counterclockwise direction, times the radius of C, plus M, both of those being in the counterclockwise direction. And since they're in the counterclockwise direction, that's going to be positive. So that's the net moment. That, of course, will equal I alpha. But more importantly, the net moment is going to give me L1 plus the integral of FNAC RC plus M dt. These are all in the positive k hat direction. And this will equal L2, and since it's coming to rest, that's going to be equal to 0. Now I don't know what the normal force is between A and C, or B and C for that matter, but I do know what M is. So this is unknown, but this one is known, and I don't know what the time is. I also know that everything inside this integral is constant, and so I can write L1 plus FNAC RC plus M, I better subscript that with a C, times T, or delta T if you prefer, let's call it delta T. That's going to equal 0. Alright, so I don't know delta T, I don't know FNAC. Everything else here is known or can be calculated very easily. Now the next thing I want to do is I want to look at gear A. Now if I look at gear A, there's a frictional moment, but I want to consider what direction is gear A moving. Since gear C is moving in the clockwise direction, it's going to push gear A in the counterclockwise direction. So omega for A is in that direction. Now omega A and omega C are not the same, but we will find the relationship between the two. And since it's rotating in the counterclockwise direction, friction must be acting in this direction. So let me label that M sub A. I better label that M sub C here. So as I look at the moments acting on gear A, there's going to be a counterclockwise moment due to this force. So FNAC times R sub A. But there's going to be a clockwise moment, M sub A. And again, I know what M sub A is. I don't know FNAC. But there's an integral here with respect to time. And when gear C stops, so will gear A. So this final momentum will be 0. So let me add in an L1A for the initial angular momentum of gear A. But I can calculate that out. That's not going to be difficult to do. So the idea then is that this equation will become L1A plus FNAC R sub A minus M sub A. Again, these are all constants, so they come out of the integral. Delta T is equal to 0. So I don't know delta T, I don't know FNAC. What I end up with here is 2 equations and 2 unknowns. I could look at gear B, but I'm not going to gain any information because gear B is identical to gear A. And so all the unknowns are exactly the same. But it's not a problem because I've got 2 equations and I've got 2 unknowns. So let's take a look at these 2 equations again. First off, L1, that's the angular momentum of gear C. Since I know the mass of gear C and the radius of gyration, I can find out what its rotational inertia is. So as I examine gear C, the rotational inertia of C is equal to the mass of C times the radius of gyration of C squared. But I know both of those things. In addition, I do know omega of C. That was given as 2,000 RPMs. So that's going to be 2,000 rotations per minute, which I can multiply that by 2 pi. That's going to be 4,000 pi radians per 60 seconds. And that will give me my angular velocity for gear C in radians per second. In addition, since the velocity at the edge of C is in contact with gear A, then that must equal the velocity at the edge of A. Well, omega sub C times R of C is equal to the velocity of C. So this is the radius of C times the angular velocity of C. And this must equal the radius of A times the angular velocity of A. So the angular velocity of A is going to be equal to the radius of C over the radius of A times the angular velocity of C. And so given all this information then, my impulse momentum equations become the mass of C, which I know, the radius of gyration of C squared, that's I, times omega of C, which I know. That's going to correspond to my L1, plus FNAC, which I don't know, times the radius C, which I do know, plus the frictional momentum of C, which I'm going to label that way, times delta T, that's equal to 0. Again, in this equation, I don't know FNAC and I don't know delta T. Everything else is known numerically. And then as I look at gear A, I get the mass of A times the radius of gyration of A squared, which I know, times omega of A, but that's the radius of C over the radius of A, times omega of C. Everything there is known, plus FNAC times the radius of A minus the frictional moment of gear A times delta T, and all of that's equal to 0. And again, in this example, I don't know FNAC and I don't know delta T. So I have my 2 equations and 2 unknowns, and they're all linear, and that can be solved pretty straightforward.